In the last lesson of this unit, we're going to analyze graphs of polynomials. So we're going to talk about some definitions here and some wording that maybe we've already used already in this course, in this unit, but just to kind of solidify your ideas and your thinking on the different definitions you see. So here we have a polynomial, and you can see the polynomial, and this is just in general. So we've seen this before back in the first lesson. So we have and the following statements are equivalent, which means that they're equal. So if you have a 0, then you know that just some variable k, that will be a number, so it could be 2, it could be -3, is called a 0 of the polynomial. And then we have something that's a little bit different. It's called a factor. A factor is when, remember when you multiply things together, they are called factors. So here we have a factor, and that would be x minus k. So our 0 is just k, and our factor would be x minus k. And then a solution's pretty similar to a 0, so zeros and solutions are pretty much the exact same thing. So k is a solution of the polynomial if we were to set it equal. So if you had a polynomial equation and we set it equal to 0, so f of x equals 0, k would be considered a 0. And then an x-intercept, if k is a real number, k is an x-intercept, so we have a definitive x value where it crosses the x-axis. So here we have the graph of the function passes through k, 0. So we've been talking about this all along throughout this unit. So again, these are just some different wording of talking about the same thing. So here's a new concept. So here we have a y-coordinate of a turning point. So we actually look at the actual y-coordinate is what we call a local maximum. Or usually we just say it's a local max. Sometimes you'll hear the word relative, which would mean the same thing, if it's higher than all the other nearby points. So think about if you have a chain of mountains, the very top of those mountains are the highest point of a specific mountain. So if you had your mountains here and you had a bunch of different hills, different mountains, there can be different maximums because they each would have their own top of the mountains. So that would be a maximum. This is a local maximum because according to all the other points around it, it would be a maximum. So there could be multiple local maximums. The y value is called a local min or a local minimum if it's lower than all the nearby points. So here we have a minimum, a minimum, a minimum. So you have a couple different mins that you have, again, if it's lower than all the other points. So if it's in the valley, would be considered a minimum. Again, sometimes it's called a relative minimum. So let's see, what do we have next? So here we have a little bit of interesting facts about turning points. Now, again, it's not something that you need to memorize, but when we look at graphs, then it'll kind of come back to these 2 points. So for number 1, the graph of every polynomial of degree n has at most n minus 1 turning points. So if the degree of a polynomial was 6, it's not the highest turning points that it will have. It won't have any more local maxes and mins than 6 minus 1. So it will have at most 5 turning points. So they are your local maxes and mins. And then if a polynomial function has n distinct real zeros, so this one is just talking about real zeros, not imaginary zeros, then its graph has exactly n minus 1 turning points. So we have the word at most and exactly, which defines the two separate ones. So we have ones that are degree n, that would include your imaginaries. And in number 2, the difference here is that you're talking about real zeros and not your imaginary solutions. So in this course, in this last lesson, we are going to just sketch some polynomials. We're not going to really worry about your mins and your maxes exactly where they are. We just want to make sure that you get a good idea of what they would look like when graphed. At this point, you've already kind of sketched a bunch of them, so it's just piecing together what you've done throughout the unit. So we're going to start by using a number line. And on the number line, the shaded parts represent the positive outputs. Positive outputs are your y values. So if they're positive y values, that means you're going to be above the x-axis. So your graph would be located at that point when this number line is shaded. So if I take a look at this first number line, let me zoom in a little bit. We have some shaded parts here, so I'm going to put pluses and minuses so that we know if it's positive or negative. So all the way here on the far left, we have a shaded region. So since it's shaded, I know that that part's going to be above the x-axis. So I'm going to put a plus sign because my outputs are positive. In the next section, between -3 and 1, I can tell that it is not shaded because it's not shaded, so I know I'm going to have negative outputs. So I'm going to build, my function is going to be below the x-axis. And then between 1 and 4, so this part right in here, it's shaded, so I'm going to put a plus sign because that's going to be above the x-axis. And then in this last section from 4 on up to infinity, it's not shaded, so it's going to be below the y-axis. Usually when I graph them, I usually just do the pluses and minuses, but sometimes people like to shade. It makes it a little bit easier for them to see. So what this does is this gives us our zeros, our x-intercepts, -3, 1, and 4. So I'm going to plot those intercepts on my graph. Bring it over here. And again, this is just a sketch, so I'm just going to approximate where my x-intercepts are. So 1, 4, and -3. So now we know that if I look at my number line, I see over here I have a plus sign to the left of -3. So that means that my function is going to be coming from above the x-axis. So it'll look something like that. And then in the next section, it has a minus sign between -1 or -3 and 1. So that means my function is going to drop below the x-axis. So I'm going to draw, I just drew a little segment here so it was below the x-axis. And then between 1 and 4 is a plus sign. So it's going to be positive outputs. So between 1 and 4, my function is going to be above the x-axis. And then the negative sign from 4 to infinity means that my function's end behavior is going to go down. So now looking at this graph, you may recall that we've discussed the end behavior before. Just looking at a graph, we can tell a few things. We can tell that the degree of this polynomial is going to be odd because the arrows go in different directions. And I know that the leading coefficient of this equation would be negative because if I look at my right end behavior, it's going to -infinity. So a few things that I know. You can also calculate the minimum degree. If I look at this graph of what I see, if I count my direction changes, this is kind of goes with your turning points. I'm going to just trace along. So here's 1, 2, 3. So I have 1, 2, 3 sections there. That means that my degree is 3, which makes sense because this was an odd degree polynomial. So for the next one, so off on the far left is shaded, so that's going to be above the x-axis, so I'm going to put a plus sign. And then in the next section, negative 4 to 0 is negative, so I'll put a minus sign. And then I have two sections that are shaded, so they're going to be above. They do have a 0 and x-intercept in between them, so that'll look a little bit different. You do have to include both of them because that 3 is important. And then on to the right side behavior will go down to negative infinity. So even just looking at my number line, I can figure out even versus odd, because if I look here, I have a plus sign on the left and a negative sign on the right. So I know that my polynomial is going to be an odd degree polynomial because they go in different directions. And I also know that my leading coefficient is going to be negative because my right end behavior goes to negative infinity. So we'll plot those points on my x-axis. So negative 4, 0, so right there at the origin, 3, and 5. So the first part, I'll come above the x-axis. Try to draw that a little bit better. And then from negative 4 to 0, I'm going to be below the x-axis. And then from 0 to 3, I'm above the x-axis again. So it is important that we stop here at 3 because there is a definitive 0 there. And then again, we're at above the x-axis. So it's going to bounce off that x-intercept. And then from 5 to the right, the end behavior is to negative infinity. So if I look at this right here, I can tell that I have a double root. A double root is when you have, let me zoom in on the graph so you can see it here a little bit better. The double root is found when you have what looks like a quadratic. So if I were to, let me highlight just this quadratic so you can see. So right here is a quadratic function. That's considered a double root. So when you were to see that in an equation, that would be an x minus 3 as the factor, because remember 3 is the 0, x minus 3 is the factor. And then that would be squared because you have a double root, meaning, again, it's just a little quadratic. So again, we can figure out, we've already discussed, it's an odd degree because they go in different directions. The leading coefficient is negative. So you can get a lot of stuff just from looking at the graph. And then this last one, we have above the x-axis all the way to the left. And then we have below the x-axis because it's not shaded. Below the x-axis is not shaded. And then above the x-axis is shaded. So on the far right. So just looking here at my number line, I can pick out the double root. So right here in the middle, I have a negative and a negative. So I can tell that 2 is going to represent a double root because I'm going to just sketch this here. You don't have to. This is going to be below the x-axis. It's going to touch 2 and come back down below the x-axis. So that would look like a quadratic right at the x-axis. If you look at, I'm going to go back up to this number line from the second problem. I can also tell that that would be a double root if I could make it look a little bit nicer. So it's going to come in, touch the 3, and go back above the x-axis. So the double roots you can find on the number line because they have the same sign to the left and right of them. So I can tell that negative 2 is not a double root on this graph because on the left of negative 2 is a positive and on the right is negative. So it's going to transfer and it's going to go right through the x-axis. So if you look at your number line, that's how you can tell. So we're going to go ahead and plot those points. So negative 2, 2, and 4. Negative 2, 2, and 4. So on the far left, I have a plus sign, so I'm going to be above the x-axis, then I'm going to drop below. So above the x-axis, I'm going to drop below the x-axis. Remember, we have that double root at 2 because it's going to go and touch 2 and drop back down. And then from 4 to infinity, it's going to go to above the x-axis. So again, here we can figure out the degree. The degree of this polynomial is even because the arrows are going in the same direction, and our leading coefficient is positive because the right end behavior is going to positive infinity. And here are our steps to graphing. We're going to graph a few problems on the next page. Number one, you want to find the roots or the zeros of the polynomial, and then usually you plot them on the number line or the x-axis. So we're going to use a number line. If in the end, if you don't need a number line to sketch them, you don't have to. Make sure that you note any double or triple roots. The double roots and triple roots are found by looking at the exponent of the factor, which we'll do a couple problems with. List the domain intervals, that's just the number line. Pick a value from each domain interval and plug into the equation. This step is not necessary if you understand the pluses and the minuses above below. But I'm going to show you an example of how, if you're not sure of the pluses and minuses, how you can pick a value and figure it out. Determine if it's positive or negative, so that's used on the number line, and then we're going to graph it. So if we look at this first example's pretty nice because it's already in factored form. So that's typically how you want to graph them, in factored form, because it's easy to find your x-intercepts. So we can find our x-intercepts, which is the first thing we're going to do. And the x-intercepts, again, are your zeros. And since it's factored, we just use our zero product property. So you set x equal to 0, so that's just 0. So one x-intercept is 0, 0. The next x-intercept comes from the second factor, so x plus 2 equals 0. Your x-intercept would be negative 2, 0. And then your third factor would yield a x-intercept of 4, 0. So they are our 3 x-intercepts. If you look here, you can tell the degree of each one. So we don't have any double roots here because this is just x to the first, x plus 2 to the first, and x minus 4 to the first. So if that had happened to have a square next to the x minus 4, that would be considered your double root. But it's not, so we don't have any double roots. They're all single. So we know that the degree of this polynomial is 3. We know that because you just add up the exponents here, the degree of each polynomial. That's called the multiplicity. So each one has a multiplicity of 1, 1, and 1. So if you add those up, you would get a 3. You could multiply it out into standard form to figure out the degree because that would be the highest exponent, but you don't want to multiply it out because you won't find your zeros. By the way, 3 is an odd number, so we kind of get an idea of what our arrows are going to look like, our end behaviors. And then our leading coefficient, well, we could just look at the equation. The leading coefficient is 1, which is positive. So we're going to make a number line, put our zeros on it. So we have negative 2, 0, and 4. And again, we're going to take a look at the leading coefficient first. The leading coefficient tells us what on the right side is going to happen. So since it's positive, that means the leading coefficient, or the right side, will be above the x-axis. Once we know that that is above the x-axis, we use the fact that it's an odd degree to figure out on the far left, on our left end behavior, what's happening. Well, it's odd, so they're going to go in different directions. So that's going to go below the x-axis. And we don't have any double roots, so our polynomial is just going to go through the x-intercepts without bouncing back off. So double roots, you kind of have to do a little bit something different. So we have here on the far left is negative. So in the next interval between negative 2 and 0, it's going to go above the x-axis. And then between 0 and 4, it's going to drop below the x-axis. So then that is now pretty much your number line, and you go back and graph how we did on the previous page. So we're going to graph our x-intercepts. So negative 2, 0, and 4. and then we have below the x-axis, and then we go above, and we go below. Now, if you graph this in your graphing calculator, it won't look exactly the same because your local mins and maxes are probably not where I have them drawn. So right now we are just sketching. When you get to pre-calculus, you will have to actually figure out some points in between to give you some more local mins and maxes. But I'm just concerned that you can, my concern is that you can graph it. Now, I'm going to give you an idea, or a way that if you're not certain about the pluses and minuses, how you can always figure it out. So I'm going to take a look at this original polynomial. And say, I'm going to circle a section. Say I'm not quite sure what sign I'm going to put here between 0 and 4. You can choose any x value between 0 and 4. So let's see, if I choose an x value of, let's say, 2, because 2 is between 0 and 4. So I'm going to use 2. I'm going to plug 2 in for all of these x's. And I'm going to see if I get a positive number or a negative number. You really don't even care what number it is at this point. We just care if it's positive or negative. So if I plug a 2 into this first x, I'm going to get a positive, just a positive 2. Again, I don't care what the number is. I just care that it's positive. If I plug a 2 into this next factor, 2 plus 2 is 4, again, which is positive. And if I plug a 2 into this last factor, 2 minus 4, I'm going to get a negative number. And when you multiply a positive times a negative, you're going to get a negative, which, by the way, is what we have here on our number line, just knowing that single roots go through the x-axis. So again, if you're not sure about the number line and how you're going to put your pluses or minus, just choose a number in between the numbers that you're not certain of, plug it in, and see if you get a positive or a negative, and that'll help you out. For this next one, we're going to look at our x-intercepts. It's, again, already in factored form, so we don't have to worry about it. The x-intercepts from the first factor would give me 0, so 0, 0. The second factor, right in the middle here, x minus 1, its x-intercept would be 1 comma 0. And then the last factor, x plus 2, would have a negative 2 as its x-intercept. Now this one does have some double roots. We have a double root right here, so that because it says x squared. So I'm going to write dr for double root. The second one, x minus 1, is just to the first power, so that's not a double root. And then the third one is a double root because it's to the second power. So again, you just add up your, what we call multiplicities, the degrees of each polynomial, or each factor. So 2 plus the 1, that's the second factor, plus 2. 2 plus the 1, remember that's just to the first power, plus 2 is equal to 5. So the degree of this polynomial is 5, which is odd. And then we also can get the leading coefficient here. The leading coefficient is negative. So drawing my number line. I'll put on the number line my zeros. And then we take a look at the leading coefficient is the first thing we do. So the leading coefficient is negative, so I know that to the right of 1 is going to be below the x-axis. And then we look at the odd degree and know that they're going to go in different directions. So this on the far right is negative, so on the far left will be positive above the x-axis. Now, I always start from the left at this point and go work left to right just as we read. So I want to look at the 0, negative 2. Negative 2 is right here, and I know that it's a double root. So that since it's a double root, I know that whatever's on the left of negative 2 is on the right of negative 2, because it's going to have to look like that. And then 0, so I look at 0, which is the next 0. And 0 is also a double root. So I know that that is also going to be positive because it has to, again, go in and touch and come back to above the x-axis. And then 1 right here is not a double root, so it's going to go right through the x-axis, which we already have that minus sign there, but it's going to kind of look like that. So if we go ahead and put that on our graph, -2, 0, and 1. Do your best there in the center, maybe if I zoom in a little bit. So let's see. We have above, then we drop below. So you're going to be above your double root, another double root at 0, and then it's going to drop below from 1 to infinity. So here we have a couple mins and a couple maxes. Again, if you were to plug this in the graphing calculator, then it wouldn't look exactly like this because of those mins and maxes here will not be exactly where I have them. But you should have your double roots here at -2 and 0. So this next one, we have your x-intercepts doing the same process. Your x-intercepts would be 0 from the factor out front. So 0, 0. -1, 0, which happens to be a double root because it's squared, 1, 0, and 4, 0. And then we look at the degree of the polynomial. So we have an x to the first, so that's 1, plus 2, plus 1, plus 1. So 1, 3, 4, 5. So it's a degree 5 polynomial, which is odd. And the leading coefficient in this one is -2. And all I need to know is that it's negative at this point. So we fill in draw our number line, put our zeros on there. So we have -1, 0, 1, and 4. So on the leading coefficient, again, is where we start. The leading coefficient is negative. So that means on the far right, it's going to be negative. It's odd, so my opposite side will be above the x-axis. And then again, I start from left to right. So here I look at the first 0, -1. And -1, it is a double root. So that means that to the right of -1 is also going to be positive. 0 is not a double root, so it's going to go right through the x-axis. And then 1 is also not a double root, so it's going to go through the x-axis. And then 4, we already know, but it's not a double root, so that's why it goes from positive to negative. So let's take a look at the graph, plot our points. So we have a point here at -1, 0, might have to zoom in to graph this a little bit better, 1, and 4. So when I graphed this, we were above the x-axis, and then that was your double root. And then we went below, above, and then we dropped below for an end behavior that was negative. Now the only thing, that word of caution I would give you, is make sure that you keep this nice and smooth. The definition of a polynomial is that they're smooth and continuous. So when you draw in, it's very tempting. I'm going to do this off to the side, but don't draw this down. It's very tempting to do it one at a time. So you come in, and then you have a double root, and it looks like that. Right? You need to make sure that your polynomials are smooth, so it's a nice parabola. So go back and round your edges out once you're done. Okay, so you don't want any what we call cusps. A cusp looks like this. So you don't want anything like that. So again, I understand why you do it, but just be careful. So let's see. And the last one. So the last one here, we have a zeros, or your x-intercepts. 0, 0, which is what we call a triple root. So if I look here at this factor on the outside, it's 0 is 0, but it has a 3, so that's considered a triple root. The only time a triple root looks different is on the graph, so we won't worry about the triple root until we actually go to graph it. Negative 3, 0, which is a double root because it's to the second power, and 4, 0, which is just a single root. Again, the triple root will look, you can't even tell a triple root on the actual number line itself. So let's see, we have 0, negative 3, and 4. Oh, forgot to do the degree. The degree is going to be in this one 3 plus 2 plus 1. So that would be 5, 6, which is even, with a leading coefficient that's negative, because it's negative 2. So on the far right is going to be below the x-axis. It's even, because it's a degree 6. So if the far right is negative, on the far left is also going to be negative. Negative 3 is a double root. So right here, around negative 3 to the left and to the right will have to be the same sign. So that'll be negative. 0 is not a double root. It'll go right through the x-axis, and then you have your number line complete. And the last thing to do is to graph this. So plot our x-intercepts. So negative 3, 0, and 4. So let's see, on the far left, it was below the x-axis, and then that was a double root. And now at 0, it was a triple root. The way that you draw the triple root is it will look like what we call a cubic function right in the center there. So right at the center on the x-axis, you'll have what looks like to be a cubic function. And then we went above and then back below. Cubic functions, again, they look like this. And right here in the center is what we call the point of inflection. And that's when it goes from opening up to opening down. It's concave up on one side, concave down on the other. It could also look like this. And right in the center would be that x-intercept.